That's always a good sign. Yeah, perfect. Yeah, it must be, it is. It's Windows 10. It's a good thing it's not Windows 95, otherwise it would not happen. Morning. Well, anyways, while this is firing up, maybe I'll talk a little bit about myself here, how I got to speaking to you all today. So, as Ron mentioned, I am an employee at a small company here in Santa Barbara called Freedom Photonics. We're about 50 people big right now. And, life wasn't difficult enough, so I decided to go back to school to get a PhD in photonics. And I'm currently going into my second year. And the question always arises, when are you going to finish? And it's a moving target, but hopefully maybe within about 2 years I can complete that. But tonight I'll be talking a little bit about some of my research and also some of the things that we do also at Freedom Photonics. There we are. Okay. Well, thank you again, and good evening, ladies and gentlemen. So, as already mentioned, I'm Steven Estrella. My talk tonight is a little bit more longer than the original title, but Astrophotonics, photonics for investigating Earth and the cosmos. So a little far-reaching, but we'll see if we can do some justice tonight. Once again, I'm from Freedom Photonics and UCSB. I think I hold the longest title there, but that's a great thing. So just to give you a little motivation where we're going to head tonight, maybe a lot of you probably haven't heard the term of astrophotonics, so I'm going to define that a little bit for you and give you some examples of how my world in photonics is a little bit related to astronomy. I'll get into how photonics is used for observations, mainly using optical telescopes. Photonics is also used for earth science, and I would put that under the umbrella of astrophotonics. It's also used for space communication systems. That's also something we're pretty active in, so I'll touch on that. And then, of course, some of you have probably heard the buzz of quantum computing, so I couldn't help resist myself to touch on this, but it is actually related, and so we'll see what that brings. All right, so astrophotonics, what does this mean? Let's take apart this word. So astro, I'm sure many of you are aware, astronomy is the study of objects and matter outside of our atmosphere, looking at some of their chemical properties, and something like astrophysics, which is really a sub-branch of that, looking at some of the physical properties of celestial objects. So the question is still, what is photonics? So of course, my favorite place to start here is looking at Maxwell's equations. I hope you all brushed up on your E&M before you came here. That's a joke, not required. We're not going to deal with any too many large equations, but it is one of my favorite places of study, beyond that. So according to Wikipedia, photonics is the physical science of light generation, detection, manipulation, transmission, modulation, signal processing. All of these terms here basically to say it's a way to control light. So people ask me, what do you do? I usually say I play with lasers. But photonics is quite interesting. It's derived from the Greek word photos. It means light. And it's really meant to describe a field, again, for performing the functions I just mentioned, very analogous to electronics, the root word there being electrons. So performing functions that use electrons, that's electronics. Many of you are aware of that. Photonics is not much different. We're doing some of the same types of operations, but we're using light instead, so photons. Therefore, we have photonics. It's a nice little graphic here. It basically illustrates, this is actually an interferometer. You have little light particles coming through. And so the question becomes, is wave a particle, or is light a wave or a particle? The answer is yes. This is a fascinating mystery, and then we use these facts to do a lot of interesting properties in the field of photonics. I'll get into what some of those are. So just to give you a little brief history, it was Johannes Kepler back in 1611 who observed total internal reflection, although unfortunately he had an incorrect mathematical explanation of that. So we come to Daniel Collidan in 1842, and he came up with this little diagram here. There's actually some light that's passing through a column of water, and water is basically going into a little bucket here. And what they saw was that the water stream itself was kind of lit up. It was guiding the light. This is what we now know as total internal reflection, light fountain. It was Townsend Shallow back in this is skipping ahead, in 1957 who first described an optical maser. This is a microwave analogy to a laser, so I'm holding a laser here in my hand. And Gordon Gould in 1959 is the one who coined the term, actually, laser. The first time it was used in the scientific field. And it wasn't until 1960 when Theodore Maiman first demonstrated a laser. And so to show you what that actually was, it was based on a ruby crystal. There was a flash tube here. And every time it flashed, it would emit light into this cavity. It's surrounded by two mirrors. And it would excite these atoms in the ruby crystal. And when they become excited, they tend to emit light that they absorb. And this process, because it's inside of a mirror, the light bounces back and forth. And so we end up getting a process where light that has been emitted gets reabsorbed many times over, bounces off these mirrors, and eventually exits. And that's what a laser essentially is. It is an optical cavity where photons basically bounce around and then get amplified, and light basically comes out. So we use this. We use lasers to do various things. But another important concept is called total internal reflection. If you've been in a pool, anyone been in a pool or in the ocean? Yeah, a couple of you, okay. So you probably are familiar with this. If you are actually in the water and you look up, you can actually see the pool floor. And this is because at a particular angle, as light basically tries to escape out, it hits the surface and eventually bounces back down. And so it's this phenomenon of total internal reflection that we use to bounce light around in a particular medium. And this is the basis of fiber optics. We use little strands of fiber. They're about the size of my hair, about 100 microns in diameter across. And there are many hundreds of thousands of kilometers of optical fiber that span the Earth, that connect all of our data centers. Every time you're on your phone looking at Twitter, Facebook, what have you, chances are your information is going through one of these fibers. So moving on just a little bit now to how photonics is used for telescopes. So as you all are aware, most of you have an astronomy background here, there's a wide variety of telescopes, but they pretty much all serve one purpose, and that is to collect light. But once you collect the light, what do you do with it? So many of you maybe recognize what this is. Anyone does ring a bell to anyone?
Pink Floyd.
What's that?
Pink Floyd.
Pink Floyd, yeah. So is it art or is it science? Yes. It's a beautiful image, but it's actually it's quite a unique image because it explains some really interesting properties of light. So if we had some white light basically coming into a prism, there is a property called dispersion. And what dispersion is it basically dictates that for a certain color of light, that it gets refracted or bent at a particular angle. And it is this property that gives us this forming rainbow. It basically separates out the colors of light, some that are the redder light being traveling at a faster velocity, and bluer light was actually traveling at a slower velocity. And so if you were to look at this sort of in real time, you can see how the light is basically bending through this prism. So we use this property of dispersion or refraction to guide light on very microscopic scales to form circuits, and that is actually what photonics is. So I'll give you a little bit more about that here in just a second. But furthermore, what's also used is an optical grating. This allows us to have light to come into a surface. It has little ridges on it, and it basically performs the same function. If you have white light coming in, you can see each of these is a little rainbow that's coming off. It's called a blaze grating because of the angle on one side of it. But we can make very, very large gratings. These are often used for astronomical instruments. This was the largest grating back in 2005. I'm sure they're much larger than today. But there's probably another example that a lot of you are familiar with. Any of you know what a compact disc is? Yeah. No, exactly. They probably will never know what a compact disc is. But basically, it's the same principle. It also has a grating on that surface. And the reason why we see this rainbow effect is because the light is basically being separated into many parts. So these are gratings that we can use to analyze light. And so often this is done in something called a spectrograph. And in this case, I decided to choose a particular example that uses those optical fibers that I just showed you earlier. If you're looking at some kind of light source, say a far off distant galaxy, you can actually focus the light into these little optical fibers. Now they travel around, they go through some lenses maybe, they bounce off of that grating that I just showed you, and they basically form a spectra, and we look at that spectra on a camera. Now why might we want to do this? Well, there's some interesting, if you can look at the spectrum of light, you can actually identify some of the molecular compounds that are present, or elements, and that basically tells you about what the object is comprised of. In this case, we're looking at a transmission spectrum, but we can basically look at the sun or some other distant star and infer what kind of compounds or molecules that it's made of. So this is a common instrument that is used in astronomy, but really the connection here is that this is quite large. These are anywhere from about maybe say a cubic meter. And depending on where you might want to put this thing, it may be more advantageous to make it smaller. So there is something that we can use. It's called an arrayed waveguide grating. So it's the same principle as a prism. You basically have light that comes in on a fiber here. It again sort of diffracts out and basically separates. And each of these little fibers then captures some of that light and it traverses around. And when it gets to the end, they recombine and they image to particular points here, each one corresponding to the particular color. So it behaves just like a prism. And there's really no difference between how these work. Let's see. It's probably updating again in the background. Yeah, same function as an optical prism. No surprise there. But what do these things look like? Well, this is an image of an integrated circuit. This is something that engineers would look at on a screen. Here, each of these little pink lines basically represents a waveguide. It's about, say, a micron wide. So we're talking about dimensions that are 100 times even smaller than the diameter of a hair. But we can create designs that get made the same way that computer chips are made. It's the same process. And here I'm showing an example of something that's about 16 by 7 millimeters. This is very, very, very small. Smaller than the size of a dime. And mind you, I just mentioned that typical gratings are on the order of, say, about a meter. So there are folks out there who have envisioned systems where you have light from a telescope that can enter into some fiber. There are some optical filters to get rid of, say, resonances or absorption due to oxygen. Again, maybe we're trying to look through the atmosphere. We want to basically get rid of some of that noise. And again, we have this same kind of photonic chip here. And this is that chip here. It's about 16 by 7 millimeters. And then the output of that would go into a CCD camera. So if we pull back a little bit from Earth, there's going to be a little common theme here. Most of this talk is going to be getting further and further away from the Earth, and we're not too far yet, we're just above the surface, maybe still here in the atmosphere. Another interesting function that can be done with photonics is something called atmospheric spectroscopy. So right now, what I just mentioned with looking at a grating was maybe looking off at some far distant star, but this is still based on the ground. But what if we're trying to look back at the Earth and figure out what's happening here? Well, we use the sunlight that basically reflects off of the surface. It comes back through the atmosphere. And depending on how that light basically gets absorbed, we can, again, infer what kind of compounds are present. And it just so happens that the field of photonics is very good at making and detecting light in the infrared wavelengths. This corresponds to about 1.55 microns in wavelength. Again, that's about 100 times smaller than the diameter of a human hair. So that corresponds to about this region here. This is 1.5 microns. And if we look closer at what's happening there, if you were looking through the atmosphere, there would be many of these little dips here. And that means that there are compounds that are absorbing light. Those compounds are primarily carbon dioxide, methane, maybe also some water vapor. And these compounds are of interest because they contribute to potentially warming of the Earth's surface. So there's a lot of interest in understanding what concentration levels are there, where are they present on the Earth, and then ultimately what can we do to mitigate that. So actually at Freedom we are actively working with NASA to solve this problem. So there is a vision for having a satellite that can orbit the Earth and using a laser beam to shine light down on the surface, bounces back up through the atmosphere, and look at what that spectral content is there. This is a little image of it's called a butterfly package. Does anyone see a butterfly? Does this look like a butterfly to you? Yeah? Okay, well it turns out you're an engineer, so I don't see a butterfly. Everyone calls us a butterfly, but it's really not. These are engineers who come up with these nomenclatures. But it's a really small circuit. This is about 4 millimeters long, about ½ millimeter wide. Again, this is very, very tiny. This image is taken through a microscope, but believe me when I say that there is an operational laser here. These are some little needles that come down to apply a current or a voltage to turn the light on, basically. And what we do in particular at Freedom is make lasers that are tunable. Most oftentimes, particularly like the laser I'm holding here, it emits light only at one color. Well, if you want to analyze something, you may want to have a light source that can produce many colors. And so that is what we have done here. Now, as I mentioned before, most of the work that we do is somewhat around 1550 nanometers or 1.55 microns, but it turns out that for looking at all of these compounds, being somewhere in the range of about 1650 nanometers is just about right. And this is some very recent work. This is actually something I worked on here about a year ago. We were able to demonstrate some of the widest tuning lasers possible. So each of these little lines here basically corresponds to where the laser emits light. And you can see that these are happening at different wavelengths. This is not happening simultaneously. We basically say, put in some voltage or current, and then we add in a little bit more, and then a little bit more, and a little bit more. Now each of those steps are basically taking a snapshot of what that laser light looks like. So we can use a laser then to look at all of these different compounds that are in the atmosphere, namely carbon dioxide and methane. So as opposed to having multiple satellites where each laser can only look at one compound, it is now possible to have only one satellite that can look at all of these compounds. So to give you a little taste of what is possible here, I'm going to bring up a video. This is from NASA. It might take a second. It's updating again. It probably is. Microsoft Office this time, I'm sure. But at any rate, what this video basically would show you if it were running is that the color here corresponds to concentration of carbon dioxide in the atmosphere. And this video basically would be swirling around the Earth so you can see where in time all of these carbon dioxide concentration clouds are. Now this was data that was taken, I believe, back in 2014. But this, again, is only looking at one particular compound. It's only looking at carbon dioxide. But imagine if we were able to have one laser, again, that could look at all of these compounds simultaneously. We'd be able to look at methane, water vapor, CO2, and we'd be able to see where on Earth are these, all of these emissions basically coming from. And that might help us to provide better regulations and to help curb sort of emissions that contribute to global warming. So, pulling back a little bit even further, I'm going to talk a little bit here about some work in the fields of space communications. So, traditionally, there are RF signals that beam, say, your internet or GPS signals down to Earth. And these are great, they work, but they're quite limited in bandwidth. Yes, you can watch high-definition TV through these signals, but in some cases that's just not enough. We need more information capacity. In fact, for future missions going to, say, Mars or even the Moon, there is a need to bring back real-time, high-definition video. And a traditional RF or satellite communication link is just not going to be able to provide the bandwidth that's really needed to keep up with that. So, as I mentioned already, they're used in space. They can maybe beam information between satellites or to the ground. You might find these in, say, low Earth orbit, geosynchronous orbit. Again, this is going farther away from the Earth. But we can also send information down or up, vice versa. But if we're looking at using a laser, it's particularly attractive because it's very directional. If I point a laser in one direction, the light only goes in that direction where it's pointed. If I was to point a radio wave, as many of you maybe are aware, it's going to basically spread out. And depending on what kind of information, maybe some secret information that's being passed through there, that might not be a good thing. So having a communication link that uses lasers is highly beneficial because it has high directionality. It's only going in one direction. The other benefit of that is it has extremely high bandwidth. We're talking on the order of hundreds of megabits to even up to hundreds of gigabits per second. To give you an idea, you could basically transfer, say, 1 DVD per second from here to Mars. That would be possible with such a link. But of course, as we all find a new home on the Moon and Mars, we're going to need Netflix. So that's yet another reason why we might need a laser communication link for that. But of course, none of this comes for free. There's always some cost to pay for that. It's very bulky and complex, and it's very, very costly to implement these things. But I'll give you a little bit of overview of what is kind of currently being done to address this issue. So this is some work that I did back in 2012. Here up in the top right-hand corner, this is one large chip that's made on a wafer. These wafers are about 4 inches in diameter, and you get about, on the order of about 20 of these little dies. These are about 20 millimeters by 20 millimeters, and you can see there are a bunch of gold patterns on there, and each one of those is a different type of laser. So the idea for this work was, if we want to make a very high capacity link, what would that look like? Turns out that there are many ways of encoding information in light. Some of you are probably already familiar with these and not know it. One is that you can just simply turn light on and off. That is pretty easy. On is a digital 1, off is a digital 0. We could change the color of light. We could say use red light for a digital 1, blue light for a digital 0. But we could also do other things like changing the phase of light, which basically has to do with when does a passing wave crest and also peak. We could also think about changing its polarization. Some of you are maybe familiar with this from using your sunglasses. If you look at light, say, bouncing off of the ocean, you'll notice that if you tilt your sunglasses to a particular angle, all of a sudden it goes very dark. And that's because the light that comes off of the sun is not very polarized, but when it does reflect off of the surface, it maintains that same orientation with the surface. So you can imagine there are waves that basically are parallel to that surface. They bounce right up at you. And your glasses have a filter that's oriented just off of vertical. So when you turn it, it basically goes dark. So we can create a system where we have a chip that basically turns light on and off, and then another chip that basically receives this light. And those chips are basically shown up here in the top right. That is a transmitter, TX for short, and also a receiver, RX for short. And again, you'll notice that these are very, 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 very small devices. You could simply blow on these and they would fall on the ground and turn to dust, and they'd be done forever. So don't do that. But we can put these things into very, very small packages, 30 by 30 millimeters. This is smaller than the size of a credit card. And so if we're looking at putting very complex systems onto a satellite, making them smaller is very advantageous. It costs a lot of money to put very heavy payloads in space. So this is an area that we've been working on to address the issues of trying to send lots of information in space. So moving on, light can also be used for making very sensitive measurements. I think one of the most best examples of that is through LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. Now there are two of these sites. There is one in Hansford, Washington, and another in Livingston, Louisiana. And if you haven't heard about LIGO, it is actually quite an interesting story about how the ideas came to fruition. This work basically started back in the 1960s by Joseph Weber, and who came up with this idea that it might be possible if you built a really, really, really big interferometer, and I'll explain what that is in just a second. You might be able to detect some passing gravitational waves. And people thought, well, this is crazy, this would never happen. And it took many decades to be able to convince the community that this was a worthwhile experiment to build. So it has a very long history of how it came to be, but some of the notable names involved in this project were Kip Thorne. Kip Thorne was at Caltech, and he started doing some theoretical work in 1968, who basically said, it is possible, but maybe not with current technology, so we need to kind of start this work now. But they basically didn't get funded until about 1994 by the National Science Foundation. They were awarded $395 million to go off and build these two instruments. But it wasn't until about 2015 when we actually started to get some signs that there were gravitational waves. So what are these gravitational waves that I speak of? Not sure if this video is going to play or not. It's unfortunate. But if this video did work, essentially what you would see are these are basically two supermassive black holes, and they basically orbit each other, and eventually they swirl and swirl, and as they do that, they are disrupting the very fabric of space itself. And it's akin to throwing essentially like a rock into a pond, and you can see the ripples basically come away from it. And so these two black holes would swirl around each other, and eventually they would merge into one giant black hole. And it is that event that can be detected by these instruments. So the way that these interferometers work is that you have some light that basically comes from a laser, bounces off of a mirror, goes up to another mirror, comes back down, maybe goes to a detector. Another amount of light basically passes through, goes off another mirror, comes back to this beam splitter, and goes back into a detector. Now, just to give you a sense of scale, each of these, they're called arms, are about 40 kilometers long. So the image that I just showed you previously, where there are two of these LIGO sites, each of those arms, and there's two of them, are each about 40 kilometers long. It's a very long distance. And that's needed because it provides a very high level of sensitivity. Yes?
Virgo, LIGO facility in Pisa, Italy? There's three.
There's actually three, yes. LIGO and Virgo. In this, I'm only talking about LIGO in the US, but you're absolutely correct. There's another Italian counterpart. And so really what this is trying to measure is very, very small disturbances in the fabric of space. We're talking about very, very, very small changes in the position of this mirror. Now, I've been using hair as a particular example. And if you were to measure how much this mirror moves, it is on the order of about 1 micron. 1 micron. Again, 1/100th the size of a human hair, and it is through using light that we can actually measure that. It's amazing. So we're looking at a wave that basically passes through two of these arms, and this graphic is basically showing you that when they are out of phase with each other, that means that the maximum corresponds to the minimum of one wave, you get no signal. But when these waves are perfectly in phase with each other, they add up. And that means that you get light that passes through and you can detect it. So it's this mechanism that we use to measure the gravitational waves that are passing through. I basically flipped through it previously, but the first gravitational observation was made back in 2015. I think that was February 11th. No, excuse me. That was when it was announced. And so since then, we've been able to make, not we, the other astronomers, have been able to make a lot of measurements on gravitational waves, all enabled by using light. Now, as a kind sir pointed out, there are three of these. There are two in the US, one in Italy, but let's go even further from away from the Earth. There's another mission coming up. It's called LISA. This is actually out of the European Space Agency. LISA stands for the Laser Interferometer Space Antenna. I love that name, Space Antenna. It just gives me goosebumps. But actually, our company is involved in producing a couple of the components that are used for this. Actually, you can see there's some red light, basically, that's passing through. There are three of these little space probes that are all spaced out by about 2.5 million kilometers. So this is a very, 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 very large interferometer. So our company is working on the lasers that can be used in this probe, and also on the detectors. Of course, it's one thing to generate light, but we also need a way to detect it. And so this is a ways off here. There's still probably many years worth of developments to make before this can actually launch, but this is just another area of interest for us. And I just wanted to show you a quick little graphic because I think it's quite neat. These space probes, there's three of them. They basically form a little triangle, and when launched, they're actually going to be chasing the Earth. So they will have the same, or they will collectively have the same orbit as the Earth, one astronomical unit, basically following the Earth, and you see it's a kind of a tumbling pattern as it passes around. And that basically is done to kind of increase the sensitivity for looking at many waves that can come from all different directions. I've talked a little bit here about how photonics can be used for some astronomical observations, but the future it looks pretty interesting, actually. We can do much more complicated things with light today. So actually it was in 2017 when there was the first experiment of sending an encrypted signal from space. This was back in August. It was a live video teleconference between Vienna, Austria and Beijing, China. And this is really significant here because no one has even shown anything even close anywhere in the world. This is extremely far beyond what is even done in the laboratory, and it's already being flown in space. And this is happening now. This satellite is actually out there, and it's sending some secret signals. Don't know what they are. But of course, this is concerning to the US, and so because of that, we're actually investing billions of dollars into a field known as quantum information science. We're playing a game of catch-up. So I'll talk a little bit more about what quantum information science is. Before I do that though, I'd be doing you all a disservice if I didn't at least talk about quantum bits, they're known as qubits. By now, many of you maybe have heard about it sort of in the popular literature, but just to reiterate, you can have some classical bits. Basically, it means you either have a particle here or a particle there. It means you either have light on or maybe you have light off. So basically, it's just to say that there are two states. There's nothing in between. It's either there or it's not. But that's not the case in the quantum regime. There exists a sphere. This is a three-dimensional surface where it is possible to have a state that exists anywhere on this surface. And it is this that we use to encrypt information, to be also to be used for computation. And I know I'm throwing out a lot of interesting words there, but I'll get into a little bit more about that. I basically wanted to show you this because I asked my colleagues, where do you think I am on a daily basis? I spend a lot of time at my work, I spend a lot of time at school, and so you can actually express where I am by using a very simple equation. Does anyone know what the answer to this might be? Anyone want to take a guess? Where might I be on this surface? Yeah, silence. I mean, no one really knows, right? Not even I do. But there actually is an answer to this equation, and don't worry about the math. The point is that really what this is saying is that I can be somewhere in between. I'm not at a on or off state. I'm somewhere partially in between, somewhere either on or somewhat off. Maybe more of a gray state, you might say. But it's this interesting principle that we use to do a lot of different activities, and I'll get into what some of those are. So there is something called quantum computing. Our friends at Google have an office here in town, and they're actively building a computer. I'll show you a picture of what some of that looks like. But if we did have a quantum computer, the impacts on society would be transformative. It can do a lot more things than just a standard classical computer, but it's very specialized. You're not going to use it for many things. It's really good at problems of optimization. Let's say you want to find the best route to get from point A to point B, but there's many places that you can stop. It's known as a traveling salesman problem. Yep, some of you know. Or there's many variables to consider in a problem, and you have to somehow traverse this landscape and find the best solution. But unfortunately, you will not be able to use one of these quantum computers for taxes. I know it's coming up, sorry. Not going to happen anytime soon. But again, the impacts on society are very large. If we have a way to look at, say, many different types of medical compounds, we can not just do them in the lab sort of one by one, but we can do a bunch of experiments in a computer system all simultaneously. And we can do it very quickly. This would allow us to identify maybe cures for some currently uncurable diseases. Although I mentioned that it's not going to help with your taxes, it might be able to help with your stocks, making predictions within the stock market. That's a very huge interest today. Also looking at trying to optimize utilization of energy in our grid system. That's a very difficult problem. Maybe we can optimize traffic. I don't know. If you're traveling on the 101 south through Santa Barbara on a Friday afternoon, chances are not so good there. But maybe one day a quantum computer can help with that. So there are many applications where this might help. So as I alluded to already, there is a field called quantum information science. And now we're going to dive a little bit into more of what I do as a PhD student. For these quantum computers to exist, they need to be in a very, very, very cold environment. And I'm talking very cold, colder than outer space. Just to give you an idea of what some of these quantum computers look like, there are a lot of companies. Everyone and their mother is looking at trying to make a quantum computer. Intel, D-Wave, Rigetti, IBM, as I mentioned, our friends here at Google, and even also at UCSB. I think this is kind of a neat picture. It looks like an upside-down Christmas tree. But there are some issues that need to be solved here. Again, the quantum computer is actually way down here. It's actually this little chip. But in order to get this to be very, very cold, you need multiple layers of insulation. It gets colder and colder as you go to each layer. Out here, it could be as warm as room temperature, like it is now. But as soon as you get down to this level, we're on the order of about millikelvins, colder than outer space for sure. So one of the big problems here is that as we try to make more and more complex quantum computers, we need more of those qubits that I kind of arbitrarily explained. Right now, I think the current record is about 72, but current theories are that if we're going to make a real viable quantum computer, we need on the order of millions. That's a huge problem because we can't handle all of the electronics that are inside of this. The environment the circuit does not basically like being in that environment. So we have to find ways of getting that information out. Now this little red box down here at the bottom, although it indicates the placement of where that chip is, these little squiggly lines that kind of snake up all the way through here, these are coaxial cables. Maybe you use them for your cable TV. It looks very similar to that. But here I'm kind of showing just some metrics for what an electrical cable can provide. Although 10 gigabit per second sounds pretty fast, that's very broadband internet, still not quite fast enough. It has very, very, very high loss. In other words, information that basically goes through is attenuated and we may not get it at the other end. But some other more important factors are that it does not have very good isolation to the outside environment. Again, this is made of a metal. If you touch a stove, it's hot because the heat is basically transferred through something that is probably metallic. So that's not good. It's not good to have a lot of metal connections coming all the way down this quantum computer. It can mess up the environment that's here. So we can use things. Again, this is an optical fiber. I kind of showed you this earlier. This is an image of a server rack that's from Facebook. So every time you log on to Facebook, chances are your information is somehow whizzing around in here. Make sure you check privacy on that. You don't want people seeing it that you don't want to. But fibers basically can provide an enormous amount of bandwidth. Just to give you an idea, this is about 1,000 times more bandwidth than a simple coaxial cable. It has very, very low loss. Again, these cables are used to transmit information across the ocean to connect us to Europe and to Asia. And so we can basically take that kind of technology and apply it to this problem here. It's also made of glass, and glass is an excellent thermal insulator. You might find that when you pour coffee into a mug, you're not going to burn your hand because it's actually insulating you from the outside environment. So we can use this to form a system where we have multiple of these lasers that I kind of mentioned earlier. It sends light into what's called a cryostat. This is what houses maybe a quantum computer or some other sensor that needs to be cooled. And we can have a device that can be made in the same processes that are used for microprocessors. And the point here is that light basically enters into this chip. We have signals that basically turn light on and off, and those signals basically come right back out. And one of the benefits of this is that we can take a lot of the components that would dissipate heat inside that environment and move it all the way to the outside environment. This is very beneficial because it's really, really, really difficult to cool something down. So these are two areas that we're working on at Freedom. So just to motivate this a little bit further, what I mentioned was for quantum computing. That all sounds great, but to bring it back a little bit home here for your folks in astronomy, you might actually find a low noise amplifier for radio astronomy telescopes. We can also make use of these cold environments to do dark matter investigations. But primarily what this is mostly used for are focal plane arrays. These are cameras that basically look at infrared radiation. Again, These are on the order of about 1.55 microns, smaller than human hair. But just to give you an example, these are some very, very large sensors that can be used to look at very large areas of the sky. And so the hope is that we can use the technology that I'm developing to be able to make even larger cameras, cameras that have much higher resolution, to be able to look at what's happening in the night sky and hopefully make some interesting discoveries there. So, to sum it all up, astrophotonics really is about utilizing photonic technologies, and I've touched upon what some of those are. And the hope is that we can replace a lot of the instruments that are used inside telescopes and create devices that are on the sort of micron or even millimeter scales. And this is going to allow us to make very high resolution images of the night sky and be able to, say, directly image black holes, as was also recently done here. So in conclusion, I'd like to thank the Santa Barbara Astronomical Society for housing me here tonight. And thank you all for your time and listening, and I hope everyone has a good evening. Yeah, sure. Any questions? Everyone's still awake? Good. I saw that hand first.
Are you on Ariel Camino and that furthest down the street gets you back to Las Vegas?
We are. We're right next to a lumber yard, and so there are some nice stray cats who come around. But yeah, actually, what's interesting is we're so close to the train tracks. My office is on the bottom floor, that I can tell when the trains are going. I can tell what kind of train it is, whether it's a freight train or passenger train, by how much the ground actually moves. So we're that close to the train tracks. Yeah.
Freight train is heavier?
Freight train is heavier, so the ground moves a little bit more. It's not an earthquake, it's just a train. Just another day at the office.
So you're getting harmonics and resonance then, huh?
Well, hopefully it's not actually, the building doesn't actually quite reach resonance, otherwise it might collapse, but yeah.
Please, I almost Googled you because I've been watching that business office for 3 years now. You drive a school bus past.
Oh yeah, there's a school bus right there at the beginning of Aero Communo. Yeah, yep, I see them every morning.
I'm one of the drivers.
Great, you'll have to wave. Yes.
Power level, but does your space communication
Yeah. That's a good question. So the question was, how high a power do those lasers have to be if we're trying to beam information between, say, Earth and Mars? The answer is going to be somewhere on the order of about 10 to 100 watts. Very, very high power. Just to give you an example, this laser pointer is probably about 1 to 5 milliwatts. So this is about 10,000 times more intense. Yeah. Don't point it at your friends; they won't like it. Yeah. Yes. Yep. You.
At the very end, you were talking about the photo arrays and using new technology. When I heard about your talk tonight, I was wondering if that's the sort of resolution that they could use to look for exoplanet.
Well, some of you might be able to answer that question better about what kind of resolution is actually needed. But if we go back here just a second, I did have some numbers. There we go. So just to give you an idea, this type of camera right here, there's actually many of these little focal plane arrays. They're all tiled together. And this is, I believe it's about 40 megapixels for this type of camera. But there's an even larger camera, this is called JPass, and it's about a gigapixel resolution.
So do they use that in conjunction with optical telescopes?
Absolutely, absolutely. Yeah, this one I believe, so Kepler I believe is that for a ground-based telescope or is that space? Anyone know? Space, it's a space telescope. This one actually, this is for James Webb. This is about, what is this, 4 megapixel camera. The JPass, I believe this is a ground-based imaging sensor. Yes?
The satellites that were depicted, what generally is the cost of one of those satellites? And how long is their lifespan? And what kind of temperatures can the micro quantum chips or whatever withstand in space before they start to fail or wear out? Can they get overheated very easily?
So the devices themselves, yeah, can be quite sensitive to temperature. They like to be at the same temperatures that we're at, kind of room temperature. But it's not uncommon for these devices to operate down to, say, minus 100 degrees Celsius. So it's often the case, even on satellites, the electronics are on a satellite bus are not entirely exposed to space. There is probably some heating element there to kind of keep them warm from freezing over. The first question actually was cost. That's a great question. Some of our friends down the street, maybe at Lockheed Martin, might know that question better. My estimate is we're talking on the order of maybe tens of millions for these satellites. Yeah. The lifespan is usually on the order, I believe, about 10 to 20 years. It's not too uncommon there. I mean, it usually kind of depends on sort of how much fuel they have. Once they run out of fuel, they can't really keep themselves in a particular orbit, and they tend to deorbit, and they might burn up. So usually that's the case, that they're not orbiting too far out where they won't receive enough sunlight. It's that they can't keep themselves positioned, and so they usually run out of fuel. Yes?
Comment on exoplanet. It's not just resolution, it's primarily the brightness difference between the star and the time.
Right.
So that over, just the glare.
It's what's it called, like an oculus or oculation? Occultation, yes.
Just simply the flame is too bright.
Right.
In our small telescopes, you can't see the companion of Sirius when that in its orbit, when it's too close to the main body. Right now, it's near its maximum separation, and so if you work at it, you can't see the dark energy that it's just simply because of the glare.
Yeah.
If the small star is by itself, you can see it.
So maybe not so much for exoplanets, but maybe for higher imaging of other sort of distant bodies. Yeah. Yes?
I think it's moreover, it's the diameter of the optics. You have an area disk, and a lot of small telescopes, you just get too much spreading of the light, so you can't see. So what sort of optics do they have that would reflect it in or put an image on one of these arrays? How big? Like,
Well, the
the bubble is
James
like
Webb
8 meters.
The James Webb is it's well over 100 inches.
Okay.
I forget what it is.
I think it's about 3 times that.
I think the James Webb is like 17 feet in diameter, the mirrors put together.
Yeah, something.
Kepler was pretty big. It was over 100 inches in diameter, I think. That mirror, I think.
The Palomar is 200 inches, and that's what, and it's wider than Palomar by a lot.
So there are some images, direct images of exoplanets, but fewer. They succeeded in blocking the light. So anyway,
No, thank you. Yes?
Is affected at all by any kind of space radiation, maybe gamma rays, anything like that? Does that either produce a signal or cause the FPAs to deteriorate?
Absolutely. So space radiation is definitely an issue for any kind of integrated circuit, actually. There are methods that sort of engineers use to design these so that they are less susceptible to radiation. But again, this also goes to the question of sort of a lifetime of a satellite or a system. Once it basically gets irradiated too much, maybe it starts glowing, not that much. But eventually, yes, it basically can cause so much noise that you basically start to fuzz out your image and it becomes useless.
That affects life length, but not the signal to noise.
Oh, it does. Yes, very much so. Yeah. So, but it's a good thing you bring that up because that's actually an active field of research, looking not just at the electronics, but also the little photonic circuits that I was just showing you. There are also some problems associated with that too. So to realize these optical communication systems, we have to better understand sort of what those radiation effects are as well. So it's an ongoing problem. Yes?
So on a more kind of personal as well as educational.
You mean down to earth?
What's that? Let's go back down to earth. So I don't know if anybody in this particular audience would be beneficial, but perhaps it might be something that you can share with others. One, I'm curious, what inspired you to get into this particular area of focus and line of work? But secondly, I'm not aware that in the educational system that there is a degree program in this area. So what do you know about, is that something that might be coming, or how does one go about getting into this particular area of study? Is it, aeronautical engineering? Is it electrical engineering? Is it a combination? But you can answer two questions in any way that you want. One, how did you get inspired and find your way here? And then secondly, what does the future look like in terms of educational study for this particular body of work?
Sure. So how did I get interested in this? I've kind of, for as long as I can remember, be interested in astronomy. I'm definitely not an expert in that at all. But I definitely enjoy looking up at the night sky and through a telescope and seeing some of the wonderful things there. And it just so happened that I found a path through engineering, electrical engineering, in college, and that's kind of how I got into photonics. Normally you think of electrical engineers as working on sort of electronic circuits and those things, but the field of photonics, as I kind of tried to allude, is fairly new. It's been around only since about the 1960s, 1970s maybe, and it wasn't until really about the 80s, 90s, and sort of the dot-com era or 2000s when there was a huge sort of increase in advancements there. So the way that I got into photonics was really through electrical engineering, although I would say that there are many avenues. We have colleagues who work with me who are chemists, who are mathematicians, who are physicists, mechanical engineers, you name it. I mean, we basically need a wide variety of people to kind of solve these problems. And so that's one interesting fact, that you start off school in one direction, you don't know exactly where you're going to end up, but oftentimes there are many ways to basically get to the same endpoint. And actually, specifically within the field of quantum information science, actually it was just last year that UCSB kind of created a degree program sort of specifically in that. So this is very, very new. And again, it's all funded by those billions of dollars to educate sort of our own US workforce to be able to compete on an international scale. We need educated people to be able to solve these problems. Yeah.
Well, doctor, soon to be.
Thank you.
I'm trying to remember who the speaker was last year. I have some names here. Was it Dr. Omer Blaise, Timothy Brandt? Who talked about quantum mechanics, that new computer out there at the university you showed pictures of? Might have been Claudio.
Might have been Von Damme, maybe.
Yeah. Was it Wim Van Dam?
Yeah, maybe.
Okay, well, we had a talk that didn't mention much about light waves and this stuff. It didn't show that upside down chandelier you showed up there. I think I remember a room-sized thing like UNIVAC, and the cryogenics they brought up. But you did good. And when are we going to be a doctor again?
Couple years.
Hopefully sometime in 2022, maybe?
Okay.
Yeah.
Would you like to introduce your family? There were children here a moment ago.
I'd like to say hello to my soon-to-be wife, Ingrid. The date is 10/10/2020. I love it for its mathematical beauty, but she chose that date actually. But,
Did he go on his knees? Did he do that?
He took me all the way to Chile to see the total solar eclipse.
Are you kidding me?
Yeah, did himself.
And then this lady's a friend.
friend. I have a row here of some of my friends, Andrew, Ryan,
Okay, the gang there.
some of my immediate family.
Oh, there's more of them.
Yeah, my mother and father, say hello.
My God, the whole
My nieces and nephews in the back.
Oh, there's where they are. The kids left. I was going to say, I saw some rugrats running around there. Cute as all get up. There's a niece and a nephew. All right. Well, look, on behalf of the Santa Barbara Astronomical Unit, I'd like to present you with our priceless porcelain mug. We're not putting coffee in here until you take this little paper out. That's your honorarium. What do I call you? Not Doc, but on the way to Dr. Estrella. I got that down now. Thank you.
Estrella.
Estrella. There you go. Well, good luck. Invite us all to the wedding.
Star. Name your restaurant Star in Spanish, so you're actually.
Does it really?
Stars right now.
And that's your real name?
Yeah, we have a whole galaxy here.
All right, well, I think we got food. Jerry, do you want to say any closing remarks or set up the food table or help us get things going at the close? I hate to leave this place. I like it in here. Where's the food, ladies? Oh, it's in the back? Okay, you and the family go first. Lead us. Thank you very much. Lead us. Lead us.